Okay, so the point of today's exercise is to go through some examples. Before we go through examples, we might just recap some of the things that we know about static fluids. The first is that we know that the fluid pressure at a point is a scalar. It's the same in all directions, and therefore we can just define it by a single value. If the fluid is not accelerating, it can be moving at some velocity, but actually we'll consider that later. But as long as it's not accelerating, if it's moving as a steady velocity in a container so it's not physically mixing, then we know that the pressure distribution laterally or horizontally, if you move horizontally, the pressure doesn't change. So any horizontal surface that you can get to within the same fluid without having to move from one fluid to another would have the same pressure. And we also know that if we move vertically, the pressure will change by an amount given by the unit weight of the fluid, which is just the product of density and gravitational acceleration. This is always true in any fluid, but in an incompressible fluid where the density doesn't change very much, it's negligible change, then we can always get the pressure as a function of some reference pressure and a change in elevation relative to that. So if we go up, then the pressure decreases by some amount equal to the product of the height change times unit weight. And if we go down in the fluid, the pressure will increase by an amount, again, given by the change in elevation multiplied by the unit weight. And again, the weight, the density, and therefore the unit weight doesn't change. In a compressible fluid, it's slightly more complicated because this term is not constant, but it varies with pressure and elevation, and therefore elevation. The appropriate expression is that the change in pressure with depth we can get as a function of unit weight, and as a consequence of the ideal gas law, which is this portion here. This is basically pressure defined as a function of density. Then we can get the magnitude as a function of elevation for this. And you have to integrate it with respect to both the location where you are and also pressure. And we've done that in class, and we have an expression to be able to do that. So we can also use it to our benefit to be able to measure pressure changes by using manometers. And the manometer rules are that if you go up in a fluid, we subtract a pressure. If we go down in a fluid, we add a pressure. If we move horizontally in a fluid, and we don't have to exit that fluid and come back into it, then we can always get that the pressures would be the same at any horizontal location, so long as we can physically move from one to the other without leaving that fluid. If the cavity is evacuated, then the pressure in the gas will be the vapor pressure above the liquid, whatever that liquid is. And if we move up or down in a gas compared to being in a liquid, then typically the densities of gases maybe are a factor of 1,000 smaller than the densities of liquids, and so effectively we can ignore those. So those are the rules that we've learned so far, and we'll put into practice when we look at some examples. And there are 5 examples that we can take that are all taken from the text. An example looking at suction with a bucket in water, how micromanometers work, a simple mercury manometer example, a concrete step, a form for a concrete for forming a step is one example, and also the examples of slightly compressible fluids. So we'll do each of those. So one of the challenges of this class, I think, is to be able to define the problem appropriately from the information that you're given. And so this is a problem that deals with a bucket. The bucket is inverted, if you like, with an attachment to a tube. The bucket starts out level with the water with some maybe airspace above it, and then the manometer fluid is equilibrated so it's horizontal, and then the bucket is physically pulled out of the water. So that's the basic example. And as the bucket's pulled out of the water, you can imagine that if you put your thumb across this exit for the bucket, you'd expect to get a suction on it as it comes out. And so that's really what's going on here. This suction is measured in the manometer, which originally you presume starts off horizontal but modifies itself to adjust to the new pressure regime in here. And by definition, the pressure here has to be less than the pressure here because there's a column of gauge fluid above it. And so this isn't really the correct representation of the pressure in here. You'd expect actually this level to be lower than this level. However, having said that, we can still work with this initial configuration. It's just that when we calculate the value of whatever the height of this manometer column is, then it will turn out to be maybe lower than this height if that's appropriate for this particular example. So that's the outline for this. You notice that we have air in here, which was much lower density than the water that's in the cavity. The gauge fluid is different from the water, and so quite straightforwardly we can calculate what the pressure is in here, and that allows us to be able to define the magnitude of the height of the particular column. And so what we can do is we could work from this point here and work our way down through the system to be able to come up to a pressure here that we ultimately know. This pressure we know has to be equal to atmospheric pressure because it's simply connected that we can get there from this point. So by definition, the pressure here has to be equal to atmospheric pressure. So I'll just get rid of those markings. So let's do that and work from this point here. And so if we start off at this point, and we're going to end up at PB, we could write the equations that going to this point from, so it is PB maybe it's a bit confusing, I guess, because we had PB at both places, but 0. So PB is equal to 0. And we go down to this location here. We go down H and we go up 3. And so it's equal to the unit weight of the gauge fluid multiplied by going down, so we're increasing pressure, going up, so we're decreasing pressure by 3 feet. So we find ourselves at this point. We're in a gas, and so we can happily go along this direction, and we're still at the pressure that we'd find here. And now we go down a certain amount, and we find out what the pressure is at this particular location. So in other words, we're going down, so we'll decrease so we'll increase in pressure rather, and it's the unit weight of water multiplied by whatever the height is, which in this case is 2 feet. And that then equals PB, which is equal to 0. And so we don't care about this, but this is the expression that defines our behavior. If we only have a specific gravity for the manometer, specific gravity by definition is the ratio of the unit weight of a fluid, the gauge fluid, to the unit weight of water. And so we know that that in this particular case is equal to 2.5. And so we just have to recast this expression in terms of that. And so this is exactly the same expression that we have above. If we rearrange the expression to get it in terms of h, which we want to calculate as a function of the ratios of the unit weights of these, and then we end up being able to, since we know that by definition the ratio, this is actually the ratio of this is the specific gravity. I guess what's been done here, specific gravity times, oh yeah, so this is by definition just rearranging this expression in terms of the gauge fluid weights. So the one that ends up on the bottom, well, it's just rearranged, I guess. So this expression that we have here is exactly the same as this. And if we rearrange this expression here in terms of densities of water and unit weights of water and specific gravities, we get this. We know what the specific gravity is, and which is 2.5, and we end up with a magnitude of the height being equal to 2.2 feet. And of course, 2.2 feet is less than the 30 here. So it's exactly what we expect, that it's actually lower. The level of this is lower than this, which defines a partial vacuum, lower than the gas pressure. And so there are a variety of ways to do it. This is just another way of doing it, which I've outlined down here below this, but you come up with exactly the same result. And so you can do it any particular way you wish. The other question that you might ask is what's the force that you have to apply to be able to pull this up? Well, the force would be equal to the pressure that's applied in here, the pressure in here multiplied by the cross-sectional area of here would be one way to calculate it. And the other way to calculate it would be just to calculate what the weight of this cross-sectional area of this column of water was, the mass of this column of water multiplied by gravity, and that would give you the force that you'd have to apply here. And so if you wanted to, you could calculate exactly what that force was if you knew the diameter of this particular bucket. I don't think you're given that, so you can't. But you could do if you want to, either of those two ways. Okay? Okay, the next question is to look at the behavior of a micromanometer. So micromanometer is used to calculate quite accurately two differences in pressures, differential pressures between two locations, pressures 1 and pressures 2. And the way it works is to use two different fluids as the gauge fluid. So you have in one manometer, you have gauge fluid gamma 1. In the second fluid, you also have gauge fluid gamma 1. But linking these, you have a second gauge fluid which has a different unit weight. And the idea is that by using this configuration with different weights, it allows you to be able to more accurately calculate fluids. So this is the equilibrium case that it begins with. And so what we will attempt to do is to measure, define what the pressures are, the difference in pressures between P1 and P2 as a function of different levels within this. And so the starting condition that we have is this, where these are at the same pressures, and as pressures are changed, then we modify the elevation of the manometer to accommodate that. And so we start off at the same initial height in the system across here, and we change the pressures to some new magnitude, and as a result of that new magnitude, this elevation of this level goes down, so this pressure has to be larger than pressure 2, and just by conservation of volume in the system, this volume that rises here has to be the same as this volume, as it turns out, just by continuity. And so what will happen is that this level will go down by an amount delta H, and this level will go up by delta H. By measuring the height change between these, which would be 2 times delta H between here, then we can hopefully use that to calculate what the difference in pressure is between these two conditions. So that's very simply the arrangement. The other thing that will happen is that in this case, the easiest initial configuration is if you start off with this level being the same in both, then the level in the two other fluids, the lower fluid, is also starts out the same. And this displacement of this fluid by an increase in pressure will push this one down to here. And by continuity, this will rise up actually by the same amount. So this position here would be half the height of this h. And so that's the condition we begin with. So slightly different from this. Instead of starting off with this at a different level, the second gauge fluid is at exactly the same level here, which means that these would actually balance directly here because it's symmetric. So that's the initial conditions of this. So what we want to do is get an expression to be able to describe the pressure difference P1 minus P2 as a function of what the difference in elevation of these two components is. So let's start off at this point here where we have P1. And so we write P1, which is this. We can go down to an amount which is this point here by going down. So we start off here. So we go down an amount which is equal to this length minus this, which is h1 minus delta h. These two. And in addition to that, we go down an additional amount which is equal to h to get to this point. And so those are these three components. So going down from here, we go down h1 minus h, which is this length here. And we go down an extra amount, which is h, to get to here. So we're at this point here. We're in a simply connected fluid, so we can get to this point here to get to here. And we know that the pressure here is going to be the same as the pressure here. Now we go up to this point here, which is an amount h times the unit weight of this gauge fluid. We're going up, so we subtract. And the amount is the height multiplied by the second gauge fluid to get to this point. And now we have to go from this point all the way up to this surface here, which is equal to h1 plus a small amount delta h here. So this magnitude here multiplied by the first gauge fluid. And when we end up at this point here, the pressure by definition is equal to P2. So that's the manometer equation. We want to be able to define behaviors in terms of the difference in pressures P1 and P2, not absolute magnitudes, because we don't have an absolute magnitude here. So we subtract one from the other, and we rearrange. And in this particular case, we can look at simplifying this assumption, simplifying the system. And so if we look at this, then we know that the changes in these heights in the system, that delta H in these cases, they have to be equal for each of these, and it equals, in this particular case, the same as this length change divided by 2. So the volume change in this, which is equal to the area of the tube multiplied by h over 2, is the volume change. The area of the tube multiplied by the volume is this. And this clearly has to equal this volume here, which is equal to the height change times the cross-sectional area of this little pot here. And so this is the area of the pot on the top. And so these two volumes here and here have to be equal to each other. And so we can define that as a function of the two cross-sectional areas, quite straightforwardly. And if that's the case, then we can show that if the tube is a small diameter compared to the size of the pot, then by definition, this height change in the pot is going to be very small compared to this change. And so we can recognize that this is the case. And so if that's the case, then this term here is going to be very small. And so we can just set that equal to 0. And the remainder of the calculation is left in terms of the height change h that results from this. So in other words, the difference of this and the difference in the unit weights of the gauge fluid. And so just by rearranging this after we've neglected this last term, we can get the height change as a function of the two pressures and the function of the unit weight difference between the fluids. And so long as the fluids have different unit weights, we can measure this and we can calculate exactly what the pressure differential is quite accurately between them. And so the sensitivity of this, if we like to write it out as P1 minus P2, which we'd like to get, is equal to the product of the height difference multiplied by the unit weight difference between the two fluids. And so if we would like to have a large height change occur for the system, we'd like to have a large difference between these two fluids to be able to have the maximum resolution of the system. So, oh, I guess that's not right, is it? As if these are submerged. That's right. So if this is small, so if the density change is small, then a small value of this will give a large value of this, even if this is relatively small. Okay. So that's the magnitudes of the use of differential manometer, and some discussion of whether you can use it with the same fluids. You can't use the same analysis if you have the same fluids in the system. But I'll let you go through that in your own time. Okay, the third question. This comprises two pipelines. So pipeline A going into the page and pipeline B also going into the page, linked by this manometer. And so within this manometer, the host fluid in pipeline A exists to the upper portion of this linking pipe. The host fluid of pipeline B exists in the linking pipe in the manometer, with the gauge fluid between them, which is in this particular case is mercury. The fluids in the two pipelines have different unit weights, which are given here as specific weight in A of 53 pounds per cubic feet and in B of 57 pounds per cubic feet. And the other wrinkle in this is that there's an air bubble in this pipe. So as a consequence of that, since this is a gas and all the others are liquids, then you'd expect that the pressure in this point and this point in the air bubble would be the same, and so these elevations have to be the same in the manometer tube. And so we can invoke the manometer equation in the same way. We can work from A all the way through the system to point B to get the differences in pressures here. We'll go to the centers of each of the pipelines because that's what's given here, although it's not really very clear here. This is the center of this pipeline. Pressure A acts in this particular pipe, and so we start off at this individual location. Pressure A, we go to the next location and we need to go down a total height of 3 inches plus 18 inches to get to this point here. Since the unit weights are in pounds per cubic feet, it's going to be more convenient to work in feet. So 3 plus 18 inches in terms of feet is this amount multiplied by the first component. So that gets us to this point here. We know that to get to this point here, we have to first go to here. So we go down to this point here. We're moving down, so we're increasing in pressures. So we go down 6 inches multiplied by the unit weight of the gauge fluid, which is this point here. We find ourselves here. And now we want to go up to this point, so we subtract off this height, which is 6 inches plus 18 inches multiplied through by the unit weight of the fluid in pipe B. So that's this height here and this overall length here that gets us to this point. We know that the pressure on this surface and on this surface has to be the same, and therefore they have to be at the same elevation. It'll come to this equilibrium, so we can find ourselves at this point here, the same pressure. And then we can go from this particular location to here by going down a total of this is 3 inches, this is 2 inches, and so it's going down from this point here to this point here is a total of 2 inches from where we got the pressure. And so that's 5 inches minus 3, which is 2, multiplied by the unit weight of the oil in pipeline B, which is this second one. And when we end up at this point here, we end up with the pressure in pipeline B. So again, we're asked to calculate the magnitude of that. Well, we know the pressure in pipeline A, so we actually know what this is. We know what the unit weight of the fuel oil is. We know what the unit weight of the gauge fluid is. We know what the unit weight of the other oil is. And the only thing we don't know is the pressure B. Substitute the different values, and we end up with the magnitude of the pressure B given as this magnitude here. So the only important thing to realize here is that with the air pocket, the pressures have to be at the same magnitude on the surface, and therefore they have to be the same physical elevation of the fluid part. Okay? Okay, this is a question to define the behavior of a form that you fill up from the top, presumably, with concrete. And as you're filling this up with concrete, you place a sandbag as a counterweight to stop it from floating up and floating away and all the concrete spilling from the base of this. And so the question is, what is the minimum weight of the sandbag that you have to put on here to be able to make that happen so it doesn't squeeze out of the bottom? We know a few things about it. I guess we know the top must be open. We know the weight of the form is 85 pounds, so the physical weight of this. And the weight of the concrete that goes in here is 150, or the specific weight is 150 pounds per cubic feet. And if we can calculate the volume of this form, we can also calculate the amount of the weight that results and then the force that results as a portion of that. So I guess the weight, it will be equivalent to the force. So we can make a free body diagram. We know that we can resolve vertically so that the sum of the forces in the y direction are equal to 0. And so our free body diagram would be the form, which is going to be filled with concrete. And so when filled with concrete through the top, it'll have two weights. It'll have the weight of the concrete that fills it, which will be 150 pounds per cubic foot multiplied by whatever the volume is of the form. So it'll be the density times the unit weight times the volume. And the weight of the form, which we know is 85 pounds. We have, in addition to that, we have a weight of a sandbag, which is added onto it. So these are all acting downwards, so we can add all of these terms together. But in addition to that, on the lower portion of the form, we have a uniform fluid pressure acting, because it's a fluid that fills this, that is pushing up. And that has a uniform magnitude of pressure B. And so the cross-sectional area of the base of the form multiplied by this pressure will be the force that's acting upwards. And it's acting in the opposite direction to the other weights. And so this perhaps is the wrinkle in this particular expression, in that we have to figure out what B would be. And it's kind of interesting because, you know, we have a height of fluid here, which is 1 step, a height of fluid here, which is 2, and a height of fluid here, which is 3. We know that within any system, on any horizontal plane, the pressure on that plane at any point is going to be uniform. And so what is the magnitude of that pressure? Well, it doesn't matter that the form is truncated at these two levels. The actual pressure that's going to be acting is going to be equal to the height of the fluid, the concrete in this particular case before it hardens, multiplied by its unit weight, which we also know here. And so given that, the calculation is relatively straightforward. So what do we want to calculate what the weight of the sandbag is. So this is our unknown. We can calculate each of these relatively straightforwardly just by looking at what each of those. The weight of the concrete is going to be the unit weight of the concrete times its volume. And we can calculate its volume just from the volume of this step. And so that is 3 feet wide multiplied through by the area of the side of the step. The 144 is just 12 times 12 to be able to make the conversion from inches to feet. So you can check that this is actually the cross-sectional area, if you like, of this particular profile multiplied through by its width, and it comes out to 1,500 pounds. The weight of the form, we've already been told, is 85 pounds, so we have that. And the pressure of this component here is going to be equal to the unit weight of the concrete multiplied by the height of the step, which is, what is it? Is it 3 8-inch risers? I think each of these are 8 inches. So the total height of those is going to be 24 inches. 24 inches over 12 is 2 feet. And so the pressure acting at this base is a uniform magnitude of 300 pounds per square feet. And if you multiply by the basal area of this, 3 feet wide by 30 inches in length, then you end up with a total area. These combined together give you the total force that's applied as a result of that. And so if you rearrange this expression now to get the weight of the step as a function of the other 3 components, you end up with this relationship here and an ultimate magnitude of the weight of the sandbag that you have to put on there, which is not inconsequential, which is equal to 665 pounds. So the key, I think, in this question is realizing that this pressure on the base has to be uniform. Its magnitude is given by the maximum height of the fluid here, because this is atmospheric here. Clearly the magnitude of pressure here is basically equal to the height of concrete that we have here. So the pressure acting here is not 0, but it is acting as 0 here. Hence the pressure acting at the base is equal to this height. Okay? Okay, this example is very similar to the example two pages ago, 2 pages previous. If we have a pressure at one pipeline, which is known, PB, calculate the magnitude of the pressure in the other pipeline. We have a gauge fluid which intervenes in the manometer network between points A and point B. The fluid in A is the same as the manometer section in A is the same as the fluid in the pipeline or in the container. The fluid at B in the manometer structure is the same as the one in the pipeline. And so we want to be able to calculate from the magnitude of the pressure here what the magnitude is for PA. And so the easiest way to do this, of course, would be start writing the equations at this point here and work our way through the manometer to get to this point, go across here, which has the same pressure, and then go up through this manometer to end up at this physical location here. You write a single equation. We know the magnitude here. The only unknown relative to the unit weights is the pressure at this point, and it's exactly the same as the previous example. And so I won't go through that again, but you can check that you understand this just by working through this one in due course. Okay? And the solution for that is given here. Okay, we've made the point before that if we look at liquids are typically incompressible compared to gases, but we've never really substantiated that assumption. We just made the case that it doesn't change very much. We know intuitively that when we try and compress water, for instance, it really does have very low compressibility. Fill water in a bicycle pump and put your finger over the end and try and pump, and you see the plunger won't move very far at all. And so that suggests that it is low compressibility. But how low is low? So in other words, if you go to very great depth in the ocean, say the bottom of the Marianas Trench, some of the deepest points on Earth, 9-10 kilometers deep, then how far off is the calculation, assuming constant density, which is very easy, versus accommodating the compressibility of the fluid. So we'll never ask you to do something as complex as this in an exam, but let's just go through this just because we can substantiate whether compressibility of liquids really matter when we're trying to do calculations. So the basic idea is we'd like to be able to figure out if we go to very great depth in a liquid and we consider the liquid as compressible in some way, slightly compressible, then how much will the result differ from our calculation of pressure is if we just assume this expression that gamma equals constant. So that's the incompressible case. The compressible case would be that gamma is a function of pressure. Density is a function of pressure. And so how do we go about doing this calculation? Well, we know that a relationship which covers us in all cases, both compressible and incompressible fluid, is this one, as we go with depth. And so what we could do, since we know that unit weight is equal to the product of density and gravity, we can split this out. And if we rearrange this derivative in terms of the two components of pressure and depth on one side, then we can just rearrange this equation as this equation here. So we have pressure as a function of depth, and we have rho g split up between these. So that's our first step. So we also know that the definition of modulus for any system, or bulk modulus, is a function of change in pressure as a function of change in density as a function of an initial density. So this is also uniformly true for any system that we take. And so what we could do, since this magnitude we can define, what we could do is we could rewrite this in terms of pressure and density and try and use the magnitudes of this bulk modulus to be able to define the behavior of our system. So if we take this expression here and we rewrite it in terms of the pressure and density separately, where we have these derivatives of pressure on the top and density here, we can just rearrange it in terms of those derivatives. We have only density now on this side, and we can integrate it between two locations. We can integrate it between the surface at an elevation of where the pressure is atmospheric, and we can elevate it to a pressure at some depth, and at the surface the reference density is reference density 0 and some unknown density at some other depth. So merely by rewriting this expression here, we end up with this. We apply the appropriate limits. We do the integration. The integration of dp is just p, evaluated between p and 0. And so that's this term here. The integration of change in density over density is given by the log of, so 1 over density, the integral, so this is the same as density 0, density 1 over density, change in density. So the integral of this is just the log, and substituting the limits gives us log of density minus the log of density 0, which is of course the same as the ratio of those two. So this is just the result of this integral that comes out of it. And so now we have an expression that defines pressure as a function of a constant magnitude, a compressibility, multiplied through by the ratio of the densities at the surface and at great depth. And so what we could then do is we can exponentiate this, so we can divide both sides by the modulus. So this becomes 1 on this side. And we take the exponential of both sides to get rid of this log. And if we do that, then we end up with this expression here. So this defines our density as a function of a reference density on the surface, and as a function of the pressure that we find at a point at some depth in the ocean or in the water column, and the magnitude of the bulk compressibility of the liquid. So that's the first thing we have. So now we can also return back to this expression that we have of how pressure changes as a function of depth, which is equal to unit weight. So we can go back to this expression. We can rearrange that to give us change in pressure is equal to take the constants on the right hand side, which would be gravitation, let's get rid of that, which would be gravitation acceleration times depth, and we take density onto the right hand side, and we know that the density is given by this expression here, so we can put that here, and then we can just integrate this between the pressure at some limit and some other pressure P1, because now this term is defined completely in terms of a reference density, a modulus, and a pressure. So it is a function only of pressure on the left hand side, and the integral on the right hand side is relatively straightforward. And so what we can do then is we can integrate this. So we just rearrange this in terms of 1 over this is just the negative exponential of that, and this is a function of pressure. This is a constant. This is a trivial integration. It's just z evaluated between those limits. And if we complete this integration, we end up with a magnitude defined for the pressure at the new point that we want. This is the upper limit. Actually, this is 1 here, as a function of the bulk modulus of the liquid, a reference density of the liquid at atmospheric pressure, gravitational acceleration, how deep we are, which is this elevation here. Of course, the difference between these elevations, Z1 minus Z2, may be switched because of a negative sign, but this is just the difference between the elevation on the surface and the elevation at depth, because typically we take this as our sign convention, and a constant, which is the bulk modulus of the system. So now this allows us to calculate some pressure within the system as a function of, all these are constants, except for the magnitude of the depth, which we can choose, and we can do the calculation based on that. And so I won't go through the calculation, but if you use this compressible equation and calculate the resulting pressure at 6 kilometers, then you have to use this expression. This would be 6 kilometers here. You come out with, for seawater, at 61.4 MPa. And if you use just the very simple expression for an incompressible fluid, which is just the height multiplied by the unit weight, you underestimate it by something like 1 MPa in 60. So something like maybe 2%, a little bit less than 2%. More than 1% difference, but less than 2%. And so the difference really isn't that significant. So that's it. I won't go through the last one. I'll let you do the calculation of the last one if you so wish, but those are the 5 or 6 examples that I wanted to go through. Great.